Alright, so today we're going to be going over number 45 in our notebook, which is characteristics of quadratic functions. So please go ahead and write that down in your notebook and take your notes in. So that's going to be number 45, characteristics of quadratic functions. Now, when we're working these, there's a couple things that we need to make sure we understand in these problems. And the first thing I want to review with you is standard, vertex, and intercept forms. So let's talk about those three different forms. So the first form I want you to write down, and you can just write it down at the top of your page, kind of like I'm doing up here, is going to be standard form. So anything that's written in standard form is always going to look like this. F of x, or y, is equal to ax squared plus bx plus c. Now that's the most basic form. It has no parentheses in it. It's just very straightforward and clear to see. The next form is going to be our vertex form. And with vertex form, we're looking to write it as f of x equals a times x minus h squared plus k. And then the last form you're going to want to write down is going to be intercept form. So I'm going to write it above the directions here since I'm kind of running out of space. So with intercept form, I'm going to have f of x equals a times x minus a, or x minus p, and x minus q. So just keep in mind that when you're looking at these forms, you can identify what type of problem it is based off. Usually, I look at the parentheses. Like in the standard form, you look at the standard form up here, that's going to have no parentheses. The vertex form is going to have one set of parentheses, and then the intercept form will have two sets of parentheses. So when I'm looking at it, I can pretty quickly identify which form I'm dealing with so that I can see what information I need. So looking here at number 1, if you look at this form, what form are we dealing with here? Vertex form. So we have vertex form, once again, because it's one set of parentheses, right? So to graph this, what we're going to need to do is, since we're dealing with vertex form, first thing we need to do is identify the vertex. So in this problem, the vertex is going to be identified by looking at the h value and the k value. So when we pull something out of the parentheses, we're going to make that a -2. So we switch the sign. And then the number on the end will stay as it is, which is going to be a +4. So to find the vertex is pretty simple. Next, we're going to need to find the axis of symmetry, or AOS. And the axis of symmetry here is just going to be the x part of the vertex. So that's going to be x equals -2. And then once we have that information, the last thing we need to do to be able to graph this is just put in the form y equals a x squared, and then just write in our information. So here we're going to have a is equal to -1. So we're going to write in a -1 length squared. And we're just going to do that 3 times so that we can move this thing to 3 places. So when we move it, we want to move it 3 places to the right. So that's going to be 1 to the right, 2 to the right, 3 to the right. And then to figure out which way we're moving up or down, we're just going to solve the equation. So here we've got 1 squared is going to be 1. 1 times -1 is -1. 2 squared is going to be 4. 4 times -1 is -4. 3 squared is going to be 9. 9 times -1 is -9. And then once we have this information, we can go ahead and graph the vertex form. So graphing this, we'll start with the vertex. So here the vertex is -2, +4. So we're going to go left 2, and then we're going to go up 1, 2, 3, 4. We also know the axis of symmetry is going to be x equals -2, which means we'll have a dotted line going up and down -2. And then all we'll need to do after that is just go through these problems that we found over here on the right-hand side that tell us which direction to move from the vertex. So this says to move right 1, down 1. So we're going to start from the vertex, and we're going to move right 1, down 1. And then we'll reflect that across the line of symmetry. Next, we're going to move down right 2, and down 4. So we would go 1, 2. And then we go down 1, 2, 3, 4. and then reflect that across the axis. And then the last thing to do here is go right 3 and down 9. So from here, from our vertex, we're going to go right 3, 1, 2, 3, and then down 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we're going to reflect that point across as well. Once you got those points cracked, you can then connect your points. And you would have a perfect graph of this. So I'm going to pause the video now to just kind of ask any questions. So you can pause your video as well and answer any questions if you have any. And if you're good with the graphing, you can move on to the second segment of this problem. All right, so once you got this graphed, we can go ahead then and identify some of the characteristics. And some things we've already identified in this problem. So let's first start out with the domain, because the domain is one of the easiest things we've ever talked about. So with the domain of a problem, kind of think about the graph, okay? If I have a graph of a parabola like this, and I keep extending it on down, okay, no matter what, I started here, but now that I'm out to the end points, you can kind of tell that this is widened out. So if I keep going with that, it's going to continue to get wider and wider the further I go down, right? So with problems here, we know that it's always going to get wider no matter what type of parabola I have. It could be a super skinny parabola, but it still means that it's going to get wider as I go. So with that being said, if a problem has arrows on the ends, we know that the domain is going to continue to get wider and wider until it runs out of space. So what's the furthest it can get wide to the left? Negative infinity. What's the furthest it can get wide to the right? Positive infinity. So with that being said, we know that the domain is going to be exactly what we just said. The furthest we can go to the left, which is negative infinity, and the furthest we can go to the right, which is positive infinity. So with domain, that's always going to be the case. As long as it has arrows on the end, you can identify that information. Now, the range is a little bit different here. The range is going to measure how high and low you go. So I always go low first, high second. So with this particular problem, we see that the problem is going down, right? So if this keeps going down, right, how far down can it go? To negative infinity. How high can it go if it goes up to this point? How high is that? All right, if we look over here, kind of follow it over to the axis, we can see that that's at 1, 2, 3, 4. So that's going to be the highest it can go to, which is 4. Now, is it equal to 4? Is it equal to 4? Yeah. Yes, there's a point there at 4 that makes it equal to 4. So if it's equal to 4, that means we need to put a bracket around the number indicating that we do include it in the problem. Now, we don't normally use brackets, but this is one exception. This will be one time where you'll actually need to use a bracket in a problem. Now, while we're on the topic of range, we can go ahead and move to maximum and minimum. So with maximum and minimum, first off, let's just indicate, is this a max or a min? This point up here.
A max.
It's a max. It's on top of the mountain, what it looks like to be a mountain here. So we do have a maximum here, but does mountains have minimums?
No.
No, there's not going to be a minimum here because this is going to continue to go down. So for the minimum, we can say on this one that there is no minimum or none. But for the maximum, we want to indicate how high the y value goes. So what's the highest y can be equal to here? 4. And we know it's going to be 4 because of the range. The range kind of helps us identify that. So with these problems, you're always going to have a max or a min, depending on if the problem is opening up or down. All right, so the other things here we skipped is the x-intercept and y-intercept. So with the x-intercepts, we're just looking at these points that are located on the x-axis. There's 2 of them. So when we look at those 2 points, we'll start with this one over here on the right side. That's going to be at what point? 0, 0. So we've got the point 0, 0.
Hey, open the door.
And then on the other side, we've got the point negative 4, 0. So with this problem, with x-intercepts, sometimes we're going to have 2 points that are x-intercepts. Sometimes we'll have 1 point that's an x-intercept that the vertex is touching. But then we can also have times whenever the points are, or when the x-intercepts have no points. And that's whenever they are not ever crossing. So you can have some different things there. But the one thing that will stay the same on this is the y-intercept. With y-intercepts, you're only going to have 1 point. And here that 1 point is actually going to be the same as our x-intercept. So what's the 1 point that's going to cross on the y-axis? 0, 0. So with this, we've got a domain, a range, our x and y intercepts, and then we have our maximum and minimum. All right, continuing on down, we're then going to get into the interval of increase and the interval of decrease. So the interval of increase here, now with increasing, we're looking for when it goes up. So we always start on the left, read to the right. So this is the furthest the graph starts on the left, as far as we can see. So when we look at this, this is going to be moving which way? Up. So that's going to be increasing. So the interval of increase is going to start furthest to the left, which is negative infinity. And it's going to go all the way up until it reaches this point, which on the x-axis is located at what? Negative 2. So the interval of increase is going to be from negative infinity until it reaches negative 2. Now, once it gets here to negative 2, it's going to hit a resting point, a stopping point. Right? If you were riding a bicycle, you would say the bicycle rides up the hill, but then when you get to the top of the hill, you can stop. So that's kind of a neutral zone. That's not down or increasing or decreasing. But as soon as we go past this point, we're then going to start decreasing off of the hill, or decreasing off the parabola, and it's going to decrease from, once again, negative 2 until we get to positive infinity. So the interval of decrease here would be from negative 2 all the way out to positive infinity. So really, it's really easier with this because interval of increase and decrease are not too bad. Now, interval of positive and negative is when we're above, so this is going to be above, and this is going to be below. So positive is when we're above. So if we look here, above the x-axis is going to be everything that is on top. So if you look here, we have everything. I just kind of marked it there so you can see that it's above. But that's going to be from this point to this point, which is going to be from negative 4 to 0. So above is going to be from negative 4 to 0. Interval of negative is going to be everything below that. So interval of negative is going to be all this information that's below it. So with this, we know that the widest it's going to go to is negative infinity, and then it's going to reach that point at negative 4. So interval of negative is going to be from negative infinity until it reaches that point, which is going to be located at negative 4. Then, we also know that this side is going to be negative, because it's going to reach that point at 0 and continue till it gets to infinity. So that's going to be from 0 all the way out to infinity. So with interval of positive and negative, we get a little bit different of an answer here so that we can figure out the rest of our problem. All right, now, outside of that, everything else becomes pretty easy here. So if you scroll on up and you look at the rest of this, you can see the end behavior. So end behavior is kind of based on if it opens up or down. So when you were looking at this graph, did it open up or did it open down? Down. It was like upside down. It was upside down, right? Had a negative a value. So we know that's going to be when it opens down. So if something is opened downward, right, it's turned upside down. That means that as we go to the left and to the right, both y values are going where? Down. So if they're both going down, down is going to approach negative infinity and negative infinity. If it's facing up, then both of these end behaviors would be positive. Now, outside of that, we already determined the vertex as well. If you recall, we said the vertex and the axis of symmetry are located right here and right here. So for that, we would say that we're going to have negative 2, 4 as the vertex. Negative 2, 4. Up, negative 4, sorry. No, it's positive 4, right? And then the axis of symmetry would be x equals negative 2. All right, so go ahead and see if you can work on example 2. We'll talk about it as a class at the end of the period. But I want you real quick just to take some time here and work that out. That'll be your homework for today. And then I'll give you 2 more problems to finish up tonight.